both are like from the software side, right?
Yes.
But I just wanted a quick introduction of, do we have a hardware system that is running today?
Well, I'll let you talk about hardware, since
Well,
you're the physicist.
yeah, well, if you say that this is a completely new area, that's not entirely true, because quantum physics exists for since the universe existed, and maybe even before. So it's not
Fair
entirely new. The new thing is that we finally are starting to understand it, and with we, I mean the brightest scientists in the world, not including us. But it's an extremely complicated matter. The equations are relatively simple, but it's extremely hard to understand for us human beings. So therefore it's less intuitive and less easy to get started with.
So is it because we don't see it? And I mean, what's the reason? I mean, we can't really experience it firsthand. Is that
yeah? Well, we don't see it, but it influences our lives. So there are so many quantum effects that influence our life, but we don't see it. And if we try to understand it, you have to get rid of your intuition, because it's hard to think about something that's in two states at the same moment. For example, a spin can be up and down at the same moment. A wave can be polarized in horizontal and vertical at the same moment. So it's very hard to imagine that something, and then we talk, for example, about qubits, which is the quantum representation of a bit. A typical bit is 0 or 1, but the qubit can be 0 and 1 at the same time. So, and you can do lots of calculations with it, assuming that it's 0 and 1. And that's not always easy to visualize.
So what about like the hardware? So do we have a hardware system that that we can work on today?
There are different companies that are working on that. There's Google right now is, from what they're saying, is working on a piece of hardware that will have 49 of those qubits that Johan was talking about. IBM has a project called IBM Q, in which they put 5 qubits, a machine with 5 qubits, in the cloud so that developers like us can play with them. And now I think that they've put online one that maybe has 17 qubits. I haven't played with that particular one. So it's, there's a company called Rigetti in California that's building a quantum computer. Delft Technical.
Delft University of Technology is working on a quantum computer as well. I think that the problem is, and compared with classical computer, is you can't easily build this yourself in your garage. So unfortunately, that would be dangerous if it was possible. So therefore, the production of quantum computers is limited to to a few big companies or governments or organizations. But unlike how Apple was built, for example, that's going to be extremely hard with building a quantum computer in your garage with all the quantum equipment that is needed for this.
So my understanding,
example,
my understanding is that it needs to be very cold, right? First of all, that the state is, so I don't know, if you...
There's one form of, it's called superconducting qubits that Rigetti and I believe that the Google model and IBM, I know, they use dilution refrigerators that take the temperature down to, to very small, colder than outer space, to 100 millikelvin or whatever the temperature is, so that at that temperature, then you can. There's a couple of things that happens. One is that the particles, the subatomic particles, can act. They can start acting up in their quantum mechanical way, and in a way that is free of the environment, because that whole deal where if you measure something, if you measure a state, then it collapses to 1 or 0 or whatever, then if you let it interact with its environment, then its environment measures it it becomes part of the environment. So it's so the chips then are at the bottom of a dilution refrigerator that cold, isolated from the environment, and so that's quite a trick.
Yeah.
But
Okay.
that's only one way to create a quantum computer. There are other ways as well, which are not necessarily easier. At the contrary, but you can use photons and laser technologies to build quantum computing elements, components as well. But you're facing different problems there. So it's in general it's a very complex hardware issue, and well, cooling to superconducting temperatures is one of the options that's being used, but that still doesn't mean that you can do it in your garage with your fridge open. So it needs to be very, very, very cool, a few millikelvins. So.
Okay.
There's a project by the University of Sussex, and as a matter of fact, the person that's leading that project actually spoke at Devox, I believe, last year, at one of the Devoxes, and I know that at the one in UK, about what they're building, and they're using something that's not superconducting. It doesn't require that cold temperature. It uses lasers and trapped ions, and then it uses lasers to change the gates, to change the states of the qubits through gates, as well as to entangle them.
Okay. So what about the software? So what was your presentation about, and how did you? So what kind of setup did you use then?
Yeah. So I think it's clear. So the difference between classical computing and quantum computing is both the hardware and the software, but they need to be engineered to work together.
Ooh, sounds very familiar.
I have to write that down. That's a nice slogan. Yeah. And so the problem with the hardware, well, actually, it's not really a problem. It's just that it's completely different. It's much more resembles the nature, but the software that we are writing in classical computing only works with classical bits. So we have to rewrite, or we have to write new algorithms, new software. The core principle, which is applying gates to bits, still translates to quantum computing. So applying gates to bits in classical computing, for example, means I have two bits, A and B, and I have an OR gate that will be 0 if one of the two bits, that will be 1 if one of the two bits is 1. That's a classical OR gate. And in quantum computing, we have gates as well. For example, a NOT gate, which is actually, well, which is the most simple example. The NOT gate in classical computing will convert the 0 in 1 and the 1 in 0. In quantum computing, it will convert the 0 in 1 and the 1 in 0 as well. But it will also convert all the other states in between 1 and 0. So it's a gate in quantum computing is still an operation on a qubit, but it's represented by a matrix, because the state is not only 0 or 1. The state can be anything that is a combination of 0 and 1. It can be 60% probability if you measure it to be 0, and 40% probability if you measure it to be 1. And by applying a NOT gate to it, you switch those probabilities. Where I have to make the important remark that this is not really about probabilities. When we talk about probabilities, it only means that once you measure it, there's a probability there that it will be 0 or 1. But so those concepts of gates are the very fundamental foundation of the software in quantum computing. And when we were showing this in our presentation yesterday, for a Java audience, I was thinking about the analogy with, we're now working on the quantum gates, which are analogous to the classical gates applied in classical computing. And at the very beginning of classical computing, people were working with those gates to construct algorithms. We were really working, well, not we, but the people who were working on software by then, like maybe Jim. We were really working with the bits, so adding bits, XORing bits, and so on. And on top of that, people started to write languages that were more natural to human being. And one of those languages, well, we always built on top of the previous low-level languages. And Java, for example, is a language that's built on top of applying gates to classical bits. And I hope that with more experience on how we can work and combine quantum gates, that we can create higher level languages that will be more intuitive. But there's a huge area of work that still needs to be done. We're completely not there yet, but that's why it's such a great opportunity for developers to work on those quantum languages.
So it's almost, it sounds like we are going back to doing like machine programming, right?
Yeah, it's kind of, we're back to like the 1940s where computers took a whole room, where you have a limited number of bits or qubits now, and where we're inventing languages and the machine instructions to be able to manipulate that. So it's an exciting time, kind of like back in the 40s. I don't remember. I mean, I wasn't around in the 40s, but from what I'm reading about, it sounds like history is repeating itself.
Yeah, that's kind of nice. So, so do you use tools to program? I mean, how do you go about it, or do you really?
One of the main things that's used right now, especially to learn, is you build a circuit. So you would have X number of wires in that circuit that are all horizontal and parallel to each other, and each wire represents a qubit. And then, as Johan mentioned, then you can have gates, like you would drag gates onto the wires that would then evolve those qubits in certain ways to where you set them up to where they solve a problem for you. And so that's one way of doing it. And then after someone learns and becomes proficient at doing that, then you can graduate to a higher level language that would generate these circuits. And so you might use a Python-based language or a domain-specific language then that manipulates these qubits and these quantum states to come up with the answers that you want.
And for the Java developers, what we started to do a couple of days ago with Gluon is we started to work on a quantum computer simulator with a JavaX user interface that developers can then drag and drop gates and see what the results are. And that's actually, so you may wonder, why do you want to simulate a quantum computer with a classical computer? Why don't you do it on a classical computer? Well, because it requires much more CPU if you do it in the classical way. So if we have this, if you use this simulator to create a quantum algorithm, you will soon run out of memory on your classical computer, or you won't have enough power. And therefore we're distributing the workload in a cloud. So we're actually using existing cloud computing to simulate quantum computing. That will give us insight in the algorithms and how efficient they are. And if you would then apply the same algorithms on a real quantum computer, they will be exponentially faster than your simulation on a classical computer. But unfortunately, you can't order quantum computers from Dell yet. Right. So if you want to work on quantum algorithms, you need these kinds of simulators. And the one that we created in Java, well, you can think of that sort of an IDE for quantum computing, but at a very, very low level.
Nice. So is that, do you have a URL where people can find that information?
We will put it at GitHub at the Gluon at the Gluon account on GitHub, and we will. It might appear here now.
Okay, so it's not built yet. I thought it was already ready.
It is. Well, we have to. Well, we started. Well, actually, when I said 2 days ago, it's 4 days ago. But we still have to upload it to GitHub, and but it will be there. The main discussion point is still the name.
So are they? So did you present also like a specific a problem that quantum computing would solve?
Like the hello world problem for quantum computing, as we presented it, was an algorithm that was proposed in 1985 by Dr. David Deutsch. It's called Deutsch's algorithm, and it's a very simple one, but it's meant to show that classically a problem that takes more than one query against a black box that has a function in it can be done with one query quantumly. And so, it can be exponentially faster. And so then the next algorithm that we did was a variation of that called the Deutsch-Joscha algorithm, which came along about 7 years later, but generalizes it to as many qubits as you want to use. And so, so classically, you might have to do, you know, say 65 queries to get, if you had 6 qubits coming in and hitting a function, where you just need to do 1 query quantumly. And so it's that kind of exponential speed up that we wanted to demonstrate, that is appealing to this class of problems that can't really be done classically, but has been demonstrated to be done quantumly.
Okay. Yeah. Anything else that you presented in that session that you want to share?
I think in general we try to explain people that quantum computing will be important. For example, for encryption.
Okay. Yeah.
So that is a very important topic. But we also try to make sure that we don't overhype it. There will be well, quantum computing is not a solution to everything. Some algorithms will perform very bad on quantum computers. So I think the future will be a combination of classical computing and quantum computing, and it's still not clear what the best algorithms will be for quantum computing. So therefore, in our session, we try to set the expectations right, and to give an overview of which fields might benefit from quantum computing, like encryption, simulating nature, searching, finding new medicines, and so on. So these areas, the compute incentive areas, are very suited for quantum computing, and others are very suited for classical computing.
So what's the commonality? Is that there is a lot of data, or a lot of data to crunch, and that would be the use case?
One of the commonalities Johan mentioned. He mentioned 3 different areas. So one was simulating nature. So chemical reactions, drug interactions, things that because of all of the things that need to be simulated, modeled, classically, it just takes a lot of memory to be able to even model very simple compounds. But quantumly, because a quantum computer works in a quantum mechanical way. I mean, it is, you know, the memory is literally nature, and the behavior is quantum mechanical, as Dr. Richard Feynman, who kind of founded quantum computing or quantum physics. I mean, so what did Feynman? You're the physicist. Tell me what Feynman did as far as
he wrote some very nice quotes that you can use when talking to people and to look very intelligent.
There you go.
But maybe also adding to what James said about well, indeed those things where you need very heavy computations, there quantum computing is good. And I think especially if you combine it, if you took the ratio between how much computations do you need versus the output. So if you need very complex computations and the output is in one number, then quantum computing will be great. If you need just a little bit computing and the UI as output, for example, then I think quantum computing is not gonna help you a lot. So it's really, if there are so many computations needed, but the answer will then be yes or no. That is something that a quantum computer will be.
So it would be great with big data, basically. A lot of crunching of data.
Yes.
Yeah, that's totally scary.
Like searching unstructured data, that's Grover's algorithm, and then also Shor's algorithm, factoring large numbers into primes to, at some point, break RSA security. That's another. That's one reason why governments and private firms are racing to build quantum computers, because that's a real threat.
Right.
Yeah.
Okay, so on this optimistic note,
Yes.
we're not there yet, though. So that's good.
Well, we
right?
don't know. That is
Right.
one of the key issues. You don't know. Would you tell if you could break encryption? Would you tell that now in an interview? So we don't know
Right.
how far companies are, but it's definitely moving forward.
Okay, excellent. Well, thank you for this
Thank you,
leap
Yolande.
forward, right, into
Yes.
the future. So thank you for talking to us and spending the time.
Thank
Thanks.
you.
Thank you.
Thank you for watching us.